Thermal cameras are interesting to me because they see completely differently than our own eyes. We can detect the aptly named visible spectrum of electromagnetic radiation. These cameras focus on the infrared spectrum to detect heat. Every object that has a temperature above absolute zero emits radiation in this range. That's why these cameras can be so valuable for inspection, surveillance, and defense purposes. There are quite a few rendering engines that focus on simulating human vision in specific lighting conditions, basically what a conventional camera would detect, but none really have support for the thermal part of the EM spectrum, and if they do, those engines tend to be part of enterprise solutions not readily available to the public. The visible spectrum is what most use cases are interested in, so it makes sense that engines are built for it. But as an experiment, I thought I would create my own thermal camera simulation based on the underlying physics. To do this, the first requirement is that I need a camera looking at some object in a scene. I'll start by setting up a C++ project that uses a convenient OpenGL wrapper library called RayLib. It also provides other utilities, such as handling the camera projection map for me. I'll use a perspective projection camera like real life, a reasonable field of view, and set the camera to look at the scene origin when the application starts. For the simulation, I'll add separate update and draw methods to help separate the logic as the complexity increases. For now, I'll just update the camera's position when the right mouse button is pressed. I'll draw a cube from the camera's view on screen, and draw a grid as well for spatial awareness. I just have to set up the main function that starts the simulation, and then I can build the application. And there we go, I can see and move around the object in the three-dimensional scene. Currently, the camera sensor just follows the resolution of the window, but thermal cameras often have quite a low resolution and I want to have the option to adhere to this. What I'll do is add a sensor resolution downscale factor to the simulation. To use the scale requires some updates to the rendering pipeline though. Right now these draw calls are using the default render target provided by the operating system to draw our elements. A render target is just a 2D texture that lives on the GPU, and when I draw to the default one, the elements are going to end up directly in the window on the screen. I'll create a dedicated render target for the camera that follows the downscaled resolution size of the simulation. Now, I can render the camera's view to this target and then render this target to the window. I'm also adding some widgets that allow me to update the scale at runtime. I'll probably do this for most of these runtime configurable variables going forward. It seems to be working. I can see that the resolution is lower as I update the scale. I do still want the entire window to be filled, so I'll just stretch the camera render target to the size of the window. That looks better to me. A bit jagged at lower resolutions though. I might have to smooth it out a bit later. So when I call this drawCube method, how does the rendering pipeline actually know what to draw to the render target? The answer is vertex and fragment shaders that run on the GPU. I'm planning on using the GPU for most of the actual radiation simulations, so I'll have to write my own shaders. The cube I'm drawing right now is made out of vertices and triangular faces. What a vertex shader does is to calculate where the vertices are located in the camera's view. It does this by multiplying the position of the vertex by something called an MVP matrix. This stands for model, view, and projection, which means that the vertices are moved in the scene, transformed to the camera's reference frame, and then projected onto the camera's 2D view plane. The fragment shader runs after the vertex shader and is essentially executed for every pixel within a triangular face between three vertices. The fragment shader controls the final color of each of these pixels. For now, I'll set the final color of every pixel I'm drawing to red. Now I just need to tell the application to use my custom shaders instead. I can see the cube and grid and everything is completely red now. Shaders can get quite complex, so I'll introduce the functionality I use in them as they are needed. I want to be able to simulate objects that are more complicated than a cube, so I'll need a way to create and import them into my application. I decided to use Blender to create these objects and export them as OBJ files. These files are just plain text configurations of vertex positions, triangular faces, and other information. One very useful part of that other information is how it can map vertices to specific parts on a 2D texture in a process called UV unwrapping. I need a way to tell my simulation how hot the surface of my object is, so I'm going to do it by setting the RGB values on a texture to represent the surface temperatures and then wrapping that texture onto the object. I'll still work with a cube for now, and as a test I'll paint a texture surface heat map to set the cube's surface default temperature to around 50, then make the edges a bit warmer, around 100, and throw in some hotspots around the texture as well. Back in the application, I create new model and texture instances, which I can use to load the OBJ file and the texture I just created. Assigning the texture to the model like this allows me to access the texture in the fragment shader. With the sampler method, I can get the RGB values of a texture on a specific part of my model surface due to the UV unwrapping. I'll update the final color to be this value. One thing though is I just have to update my vertex shader to pass this UV texture information to the fragment shader so that it is available. Now in my draw method, I'll draw the model instead of a cube with my custom shaders. And there we see that the final color of a cube is just the RGB values of a texture I just made in Blender. With this setup, I can already start implementing more complex functionality in my shader. I'll start with changing the intensity of the colors on my object's faces based on its angle relative to the camera. This is done by calculating the dot product between the fragment's normal vector and the vector from the fragment position to the camera's position. Just to show the direction of these normal vectors, I'll render them in yellow on the cube quickly by writing this helper method. You can see that for a single triangular face, all the vertex normal vectors point in the same direction. This means it doesn't matter what face fragment we are working with, the average of all three vertex normals will always point perfectly away from the face. This behavior is called flat shading and I'll use it for the rest of the project. I'll have to update my vertex shader to pass the vertex's scene position to the fragment shader, as well as the vertex's normal vector. I'll add the functionality to the fragment shader by using the built-in dot function and multiplying the final color by the result. And there we can see the start of some lighting effects taking shape. As I increase the angle of the camera to the face, it gets increasingly more dim and vice versa. With all that out of the way, I can finally get into implementing the math that will back the simulation. At the core, I'll use the Stefan-Boltzmann equation. This formula simply states that the radiation emitted from the surface of a body is proportional to the fourth power of its temperature times its emissivity and a constant value. Since I already have a temperature of each point on my object's surface, I just need the emissivity. This term refers to how well an object absorbs and emits radiation. Human skin, for example, is around 0.98, close to a perfect emitter. A material such as polished aluminium is around 0.09, kind of like a mirror in the infrared spectrum. I'll add an option to the simulation so that I can control this value at runtime. Raylab makes it easy to pass values like this to a shader, and you might have seen that I've already done it with a camera position. Like that value, in my update method I'll pass the emissivity value to my shader so I can use it in calculations there. I'll add a method to the shader that uses this value to calculate the amount of radiation for each fragment by passing the temperature at that point to the function. These values will be in the order of thousands, but I need a value between 0 and 1 to set the final color. What I'll do is calculate the minimum and maximum possible radiation in the simulation and normalize the emittance between that. Due to the way I'm specifying the temperature in the texture, the smallest temperature is 0 and the max is 255. I'll comment out the angle-based lighting for now and just assign the final color as the normalized radiance. Now let's see what that looks like with a cube and its temperature texture. A bit different than before clearly. It's quite dull. This is probably due to the results being on the lower side of the possible radiance range. One thing I do want to do though is to add a sort of focus for the camera sensor. Basically configuring the minimum and maximum temperatures I normalize the calculated radiance between. This should allow me to improve the visual indication of temperature differences in the simulation to make it a bit less dull. I'll do this by adding these min and max focus values as options, and then passing it to the shader to use in its calculations. Let's see what we can achieve with this method. Using the sliders to change the minimum and maximum focus, I can see that the range of colors on the cubes gets shifted. The temperature texture right now is mostly on the lower range of possible temperatures, so this definitely helps. I'll just have to be careful about clipping radiance calculations outside of a normalization range. Next up, I'll use the fragment camera angle trick from earlier to slightly reduce the radiance based on where the camera is. Let's see, that's quite harsh. The drop off from head on to barely seeing a face is very aggressive. I'll have to smooth out the drop off a bit to make it more realistic. Practically, what I'm doing here is simulating the fact that the sensor detects less radiation from surfaces not angled directly at it, but it should still detect some radiation, even at extreme angles. The colors in the simulation aren't very exciting right now. To get that thermal camera look, I'll run the normalized result through color maps in the shader. A couple of common color palettes are used for thermal cameras under certain conditions. The iron bow palette is probably the most popular and instantly reminds me of a thermal camera. I'll use that as the default. These color palette methods I'm writing take in a value between 0 and 1 and return the color at that point in the palette. Let's see what that looks like. That seems much better and shows the differences in measured radiance more intuitively. I quite like this white hot and black hot palettes. They are often used in defense and surveillance applications. I can only describe them as being easy on the eyes. I quickly exported the Blender mascot and created a rough temperature texture for it so that I have another model to look at while developing the simulation further. With this more complicated model, the camera angle trick still seems to be working well, but the radiation we're measuring at the sensor is very perfect right now. A real sensor would experience noise, so I'll add some fixed pattern and temporal noise to the calculated radiance result. Just have to pass these options to the shader once again. Since the noise values I calculate in the shader are somewhere between 0 and 1, I'll add them to the normalized radiance. These defaults seem to work well enough. I can also increase the amount of noise at runtime to illustrate the effect better. It's already starting to look much more realistic. So currently, my object is just within a void and my sensor is only detecting the radiation the object emits. The state of the air around the object can actually have quite a large effect on how much of its radiation actually reaches the camera sensor. The air absorbs some of this radiation based on the density of the atmosphere and emits its own radiation, as it also has a temperature above absolute zero. I'll model the atmospheric effects in two steps. First the air between the object and the sensor, and then the air everywhere else. The amount of radiance that survives will travel from the object surface to the sensor is calculated with something called the transmittance of the atmosphere. This value is also used to approximate how much radiation the air between the object and the sensor contributes to the measurement. The transmittance calculation is essentially an exponential decay formula based on how far away the object is from the sensor and how dense the atmosphere is. I'll add an option to the simulation to control the atmospheric density as well as the air temperature and pass it to the shader. The value for the density of the atmosphere is typically between 0.005 and 0.1, with the former being akin to a clear day and the latter to heavy fog. In the shader, I'll add a function to do this transmittance calculation and attenuate the calculated radiance with it. The air between the object and the sensor is modeled as a volume and not a surface, but I can still use the radiance equation to calculate how much radiance is emitted by it. This is done by setting the emissivity term to 1 and calculating the result. I can then multiply this term to 1 minus the transmittance value and add it to the final result. This operation is an approximation for calculating the total radiance emitted by the air particles along the way to the sensor. Let's take a look. The effects aren't very apparent with these default density and air temperature values, but as I update them, I can see that the results are changing. When increasing the density, the object slowly becomes slightly less clear as more radiation is absorbed on the way to the sensor. Increasing the air temperature results in the emittance hitting the sensor becoming larger, as the increased temperature of the air is contributing more and more radiation, even though the object's temperature is staying the same. And now for the air everywhere else. I'm going to model this portion of contributing radiation as a sort of air box around the object like this. To calculate the amount of radiation from this, I'll use the same equations as before. I'll use the radius of the air box as the distance value in the transmittance equation, but set the radiation it attenuates to 0, as outside the air box I still have the void, which doesn't contribute anything. The equation is then simplified to just this: 1 minus the transmittance times the air radiance calculated by the Stefan Boltzmann equation. This is a very simplified model of atmospheric radiation, but it will do the job for this project. Practically in the simulation, this requires another update to the rendering pipeline. I'll create a dedicated shader to handle the airbox radiance calculations, and an option to the simulation to set the airbox's radius. The shader uses the same formulas, noise and color palettes as the model shader, but simplifies the actual radiance calculation as I don't have to do any texture sampling or camera and fragment position modifications. I'll use this shader by passing the empty camera render target to it. Every pixel on the target will then get treated as background air. After this, I keep the previous model shader simulation and draw it over the air box's radiance result. There we go. Now I am simulating the background air box's effects as well. You can see now as I mess around with the air temperature and air box radius that the background radiation the sensor detects changes. Just a quick note about the emissivity of an object here. You'll remember that I said that a lower emissivity is like a mirror in the infrared spectrum. But as I decrease it here in the simulation, something weird happens. The object simply becomes a silhouette. This is not really what I would expect, but does make sense due to how the simulation is set up right now. Because I am not simulating any reflections, the object effectively emits less and less of its heat as radiation as the emissivity is decreased, becoming darker. What I'll do is slightly mangle the radiance calculation for the model to simulate the airbox radiance reflecting off of the model to the sensor. I'm doing this by also performing the airbox radiance calculation in the model shader and then mixing the calculated radiance between this and the simulated radiance based on the object's emissivity. This implements a crude simulation of atmospheric reflections off of low emissivity objects, but I think it's adequate for this project. Now in the simulation, the object slowly disappears into the background as I lower its emissivity. One more thing I'll do for the simulation is to add some blurring and smoothing effects to the final product. This is mostly just to simulate how a real thermal camera sensor would read the incoming radiation. It would definitely not be as clear and discrete as it is right now. I'm adding 3 new shaders to do this. 2 that will do a Gaussian blur, split vertically and horizontally for performance, and 1 for a type of anti-aliasing that helps remove some jagged edges on the object. Adding these effects require what is known as post-processing, and as a result I'll have to update the rendering pipeline yet again. When smoothing is enabled, I apply it to the output radiation simulations on the camera render target. Just before the camera target is copied to the window, I'll apply the blurring. I do want to apply the blurring to the post-stretch version of a camera target, so that required me to add a new final render target. These options make a big difference to the output of a simulation. It now looks much more like something you would see in real life, as the results on the sensor aren't pixel perfect as it was before. Now these focus range sliders do the job to accentuate the differences in radiance detected from the object, but they are getting a bit tedious to use. What I really want is for the application to adjust the focus range automatically, like the autofocus you would see on a real thermal camera. Practically, what I want is for the full color range of a color palette to be used at all times. I'll start by defining a minimum and maximum supported temperature in the application. This is 0 and 255 because of the way I use textures as temperature maps. I'll create another render target where I do the existing radiance calculations, but always use these minimum and maximum supported values as the range to normalize between. I'm setting up this new render target to always be 16 times as small as the camera target. This is just for performance reasons, as the calculations I'll be doing on them is going to get expensive. I'll add another special color palette setting to the shader that sets the final color just as these normalized values. What I'll do now is update the rendering pipeline to first do the simulations on this target. I'll draw this texture to the screen quickly so we can see what it looks like. It might look familiar. It's the same as the original pre-color palette version of a radiance simulation. This is basically a texture map of all the radiance results for the scene. And because I know the values the texture map is normalized between, I can implement the Stefan Boltzmann equation on this side of the application as well to reverse the result back into a temperature value. In my update method, I'll call this new helper function I'm writing that analyzes the entire texture map and returns the smallest and largest pixel values. I made the render target a lot smaller due to this expensive operation. Now I can set the focus temperature range based on this result. Let's take a look. Moving around the object, it's clear that the focus range changes, but the noise in the simulation is causing the analyzed min and max pixel values to jump around quite a lot. I also expected to see larger hotspots, but because a single pixel value can extend the entire focus range, this isn't the case. To fix these issues, I'll first write a sort of temporal smoothing class that just sets the tempo at which the focus values can change. I'll then update the helper method for analyzing the texture to instead do a histogram-based analysis. This means that I can adjust the focus to rather set the maximum temperature so that, for example, 95% of the temperatures in the scene are smaller than it, and then the same for the minimum temperature in the opposite direction. I also added fine grain control for these autofocus thresholds. Now it looks much better. The focus range takes some time to reach the new values, and the new calculated values result in a more intuitive look to the scene. Notice that when I move away from the object, the maximum temperature drops. This is because the total radiance on the sensor becomes smaller because the object occupies less of it. I quickly added some rotation for the object just to see these effects better. The simulation is now ready. Let's simulate some other and more complex objects. This is a fairly complex model of a soldier I got online. I spent some time painting a temperature texture for it where its clothing is the ambient temperature and any exposed skin is around 33 degrees, which should be accurate for a human. Messing around with the simulation options, I can make it look pretty convincing, and it is quite interesting seeing how the final result changes. The autofocus doesn't work that well on this model. I think the noise is just too much for the small range of temperatures I used. A possible future expansion to the project could be to rig some animations for the model, because the stillness on something like a human can break the illusion at times. The black hot color palette really shines with the scene at a distance. I can imagine a future version where multiple objects such as trees, buildings, and the terrain are simulated all at once. Creating synthetic data under these conditions might have some value. I also made this ring-like shape that has a base temperature of around 50 and then some really warm, smaller rings across it. The autofocus works a bit better in this scenario, and this ironbow color palette is still my favorite. An improvement I would like to make in the future is to have animated temperature textures to maybe simulate heat dispersing over the surface of an object. Still, I think it looks quite interesting and is fun to mess around with. And that's it for this project. Thanks for watching.